All right. Hey, everybody. Hope you're having a good Sunday. My apologies. I just finished eating my lunch. Excuse me, but we're going to get started today. And we're going to continue working through Chapter 7 of Essentials of Compilation. Our focus today is to get to the remove complex operands phase, which I think it always seemed intimidating. But after a few times, it actually has a very, I won't say simple, but it has a very straightforward goal, which is that you have to lift expressions such that they never, especially for primitives of the language, they never have a an argument to that operation that is another expression. So like it has to be at the lowest level, like it has to be a literal, like an integer or boolean or something like that, or it has to be a variable that's already been bound by a let statement. Excuse me, a let expression. So that's our goal to get to today. And I'm going to go ahead and flip over to the code screen because I wanted to talk about a few things I did after the stream last week. The main thing I did was last stream we did this limit functions pass, which was that if you have an function with more than 6 formal parameters, then the last parameter gets turned into a vector or a tuple. You can think of it like that. So what I did here was I made, so if you look at the commit previous to this, we updated expose allocation, but I didn't feel the best about the tests because what we did was we tested when you cross the boundary of 6 arguments. So what I did was like I added some other tests that cover the other conditions. So if there's exactly 6 arguments, that being the boundary, I wanted to make sure that we had, not introduced a vector that had 1 element in it. So that was this test. And then if there's less than 6 arguments, here we did 5, that it remains unchanged. So that was the essence of that change. I just wanted to call attention to that because we are going to be going into today we're going to be going into uncover get, which should be short because it doesn't change the source language, it just wraps. I believe that, yeah, so the point of that is to show which things are mutable, so that they gets marked appropriately for the passes that follow, and that's related to things like loop variables and so forth. You need mutability for that. Okay, so let's get started. Just FYI, I just upgraded Gleam. Gleam's 1.17 is out. Go get it if you don't have it. I also made sure that in our CI we have OTP 29. I realized that locally we've been running against OTP 29 for a long time, but we hadn't yet updated the GitHub workflow. And I want to make sure, I think that actions checkout can be updated. So let's go ahead and actions checkout. Yeah, there's v6. So let's do v6. No reason not to update that. And then we'll go look at the uncover get pass, and we'll see what we've done previously, and we'll get that up to date. And just to be sure, let's check on the Earl EF setup beam action to make sure that we have the latest on that. And it looks like yeah, 1.24, but usually the way this works is they have a tag which is like V1, which floats. That's 3 months ago. Let's see, 1.24 is on the same commit. Yep, okay, so we're good. So we don't need to update that. But I did do some updates on the dependencies. So this file has been updated. I've removed a tool that I used to convert from the Glee unit should syntax. So let's go ahead and make a quick commit to update these. So this is going to be update GHA workflow and some dependencies. And we'll go ahead and push that. And then we can get started on the fun stuff. So yeah, so we worked on expose allocation last time. And you know what? Let me do a real quick update of Z. And okay, cool. So we need to, based on this, we need to address the uncover get phase. So let's look at that pass. And okay, so this was going from, it's interesting, this was happening earlier. Okay, I want to make sure that there's the get bang expression. I want to make sure that that's already in our language. Set bang, but there's no get bang. Okay, so somehow it's in this one, but not in the one that where we converted variables into function references. So this is probably going to break a bunch of things, but I'm going to go ahead and add that variant here. And then we're just going to break down because we don't need to create a new language for this. Let's see here. Let's find the bugs here. Okay, so this is really just, let's do get bang. Okay, we're going to say doc concat. This is actually, yeah, concat join with doc.space, needs to be a list, and then parenthesize. So we're going to say from string get doc from string var. Easy enough. Okay, let's see if there's any other bugaboos in here. I think that some of our passes might, let's just do a Gleam build and find out. Okay, so that was sufficient. It's interesting that we had it here, and when we did the translation, or when we created alloc funref, which I believe was in the expose functions or reveal functions. Yeah, so we didn't handle get bang, which is really weird. Oh, this happens before expose allocation. That's why. Let's see. And I guess in expose allocation we had lfunref, which has function references, and it outputs this. So it, yeah, so we didn't need to cover that variant in this pass because we weren't producing it. So uncover get will handle this. So let's go ahead and update this. Okay, so this is going to immediately break things. Okay, so what we need to do here so we're going to have to, rather than yeah, I think what we need is mutable variables will be only local to the definition that they're inside. We don't have global mutables, so what we can do is rather than, because this used to be just a single body expression, what we can do is go input defs list map. This is a def. We can say let mutes collect set bang def dot body, and so this is basically, here, why don't I just do this, and we'll change this to def, and then we'll say l dot definition, and we're just substituting the body, and then we will pipe that to l dot program. So rather than doing it over a single expression, we're applying this transformation to every definition, every function definition in the program. And remember, our entry point is a function definition. It is just the main function. Okay, that's not so bad. So now what we need to do is update both of these two functions that we're calling up here with the new variants. So add missing patterns. So at this point, okay, yeah, this is there a clause? Yeah, so what we're going to do is we know that the uncover get expression is the transformation. We know that funrefs don't contain anything. So what we can do is put that in this clause and remove this bit, and just know that that's not transformed. And then we need to recurse into apply. And this will be list map. Arguments, uncover get expression vars. Okay. And I need another paren there. Okay, so the transformation is done. Now we just need to handle so we know that a function ref cannot contain any variables. So there's nothing to do there. Now we just need to, at the end here, add the apply, which is going to be we're going to do function collect set bang, pass that to set union of collect list dot fold. Yeah, I think we just fold. We're going to fold over arguments, set.new, and then that's going to be accumulator item. It's probably the easiest way to express that. Then we'll do set.union accumulator and collect set bang on the arguments. Not on the arguments, on that item. Okay, so if it's not clear what we're doing here, we're collecting all of the set bangs that are inside argument expressions, which would be a really weird place to put it, but our language allows that, so we have to handle it. And then collecting those also from the function expression, and then unioning all of those together. So you know, another way we could do it is a list map and then a final fold, but this does it in fewer steps. Cool. So honestly, that was not hard. That's pretty dang good. Let's go ahead and commit that. Honestly, though, we need to make sure that we have our tests uncommented, and they're going to break. So okay, so again, we have this thing. I wish there were a better way to do this. And obviously this is not the correct way to do it. The problem here is we have we need those other passes. Let's take a moment and think about how we might do this with use and a let assert. So we could say let assert okay p is this, and then we could say use tokens is going to be, and I'm going to unqualify this. I think it's probably better not to have it qualified. We'll say result.try, parse.tokens of input, and then we're going to say use AST is result map parse.parse tokens, and then we'll say AST Is there an unwrap like thing that panics? That would be good to know. I don't think there is. Oops, not this. I want standard lib. I think you just do let assert. Because we don't want the default value. Yeah. There's, because I was thinking like if we had an unwrap function, which is result of AE, and we want it to return A, then we would do case R, no, of OK, V is V, and then if it's error of anything, then we panic as unwrap. That's sort of what I would want, but this let assert is doing the same job. So anyway, getting back on track, we need all of the passes before this. We need shrink, we need uniquify, and like this is going to mess up the tests. I'm fully aware of that. We need reveal functions, we need limit functions, and then we need expose allocation. Okay, so that's import Gleam result. Okay, so this result and that inner result don't have the same types, error types. I think we need to back this out and do it the way we were doing before. And then that will also mean that we'll have the error right on the spot where it occurs rather than somewhere else, which could be useful. And then this is simpler. Okay. I don't, you know, I will reach for use whenever I can, but okay, so this is going to be incorrect because it's going to rename the variables. But what we can do is go ahead and make the transformation that we've done in our other tests. And definition. Shoot. So that's going to be the trailing thing. It's going to be main, no arguments, and L dot. I'm going to do import UC, excuse me, UC Lang's L fun, because we're integer t. We're keeping the, we're defining the type system only once. So, so we'll say integer t. Okay, and then, okay, so this is going to fail because we have shrink and uniquify, And I think that uniquify here uniquify is going to rename these variables, and that's going to break things. So okay, so here we're just testing a particular expression. Okay, so we probably need two different forms. What we need here is this can be parsed, and this can be program. The problem is these transformations mean that uncover get gets a different intermediate representation. So, collect set bang would have to be on okay. So I think that what we'll do is this is going to be an L dot program. So what we can do, we can say L dot program definition and we only want the body, right? Or we could just say this is P, and then since this is an expression, note that x here is going to become x dot 1. And let's do the same bit down here. P2. Let assert. Okay, and then this will be like sum dot 1, and this will be I dot 2. Likely. Okay, so now we know. Let's just look at what we know about I think this assumption is wrong. Actually, I need to recheck, but this is y dot 2, y dot 2, x dot 1, and this is not shadowed, so that's probably correct. Let's run Gleam test. Let's make sure there's no other tests. Okay. Hey, and they pass. So I did I did the manual uniquify phase on my own. Okay. So at the very least, we know that the mutable variables are correctly still being collected. And then also we know that this get bang is annotated here on this referencing this mutable variable, and so that will be sequenced correctly with the mutable sets. So, right. So, the way that this should work when we do explicate control, that pass, is that, and that this is what we did in a previous session when we were actually doing this. Loops, is that inside this expression here, this x will be read first, then this one will be set, because this statement, inside of begin, these are statements, and then the last bit is the expression returned from that begin, and that'll be read. So this will be this x will equal 2, because that's read first. This x will be set to 40, so this x will return 40, and you'll get 2 plus 40 plus 0 is 42, because the answer is always 42. Okay. That is a good place to make a commit. All right. And let's look at the diff real quick. Okay, so we added get bang to alloc funref, and then we are doing uncover get over all of the definitions in the program, and then we've updated the test. Uncover get pass for functions. Okay, good deal. You know, the other thing that we could do is, I don't think that we have, I like adding these as we go, because as long as we have the formatter for each intermediate language, we can put the phase into the UI. So let's go ahead and do that. Okay, so it would come after expose allocation, uncover get. Okay, and this is uncover get, and then pass to string. We want uncover get. They like their bangs at the end of those. Pass to string, string to pass, uncover get. Okay, and then, yep. So now we just have to go down here, and then we'll copy this, and we'll put in uncover get, and this will be uncover get. Okay. And I have this, oh, I did have it running. Gleam run, luster dev, start. Okay, so now we can go and do the uncover get pass, and let's just use that example from our test. Come on. Yeah, this one. This is good. Okay, so this says define main, let x.1 is 2, y.2 is 0, plus y.2 plus, and here's the get that gets wrapped around that. Get x.1 for explicit sequencing. Okay, looks good. Expose allocation doesn't do anything. Limit functions doesn't do anything. If we go back to shrink, you note that this is turned into main. If we back it up to type check, we still have just the expression without any name modifications. So that's pretty cool. Okay. I don't know about you, but I really find that that tool that we built, it was totally worth it. It makes it so much easier for me to visualize what's going on in our code. All right, so now we can look at remove complex operands, which is the whole point of this stream. So if you're still with me, thank you. We had to get here. There was a lot to do. Okay. And this, I think, probably, even though some of the upcoming phases are the more complicated ones, this puts us at, you know, about halfway through the chapter. Okay, so let's read this section. The primary decisions to make for this pass are whether to classify funref and apply as either atomic or complex expressions. Recall that an atomic expression ends up as an immediate argument of an x86 instruction. So this is the key realization, that the only arguments that you can have to an x86 instruction are variables which get lowered into registers or stack allocations, right? Or constants, so immediate values. So in order for that to be the case, what that means is if something is in an argument position, it has to be assigned to a variable, which becomes a register or a stack offset, or be an immediate value. So that means, I think that, and they say it here, this makes it pretty clear that funref and apply are both, obviously apply, because apply has nested expressions in it. Apply is a complex expression, right? And they say here why, in addition to just can it be put into a variable, the function application translates to a sequence of instructions, right? So you have to prepare the arguments, put them in registers, do the call, take the result out, and put it wherever it needs to go. Okay? Right, so on the other hand, the arguments of apply should be atomic expressions, right? Because those need to go into registers to be passed to the function that we're calling. They just need to be in registers. So if we're doing tail call optimization, which we will later in this chapter, then we wouldn't call, but we would jump. And those things need to be in registers before we jump. So they need to be atomic. Okay, so regarding funref, as discussed previously, the function label needs to be converted to an address using the LEAQ instruction. So load effective address, quad word, that's what that stands for. And we looked at that in an earlier section about how they intend for us to do the call. It's not going to be using a name. Different compilers do this differently. A lot of them would probably turn it into a label at the assembly stage and then jump to that label. But what we're doing is putting the address of the function into a register and then using a sort of like a function pointer like thing with looking at the offset of the instruction pointer, so that that relative offset bit, and then jumping to that, or recalling it rather. So thus, even though funref seems rather simple, it needs to be classified as a complex expression so that we can generate an assignment statement with a left-hand side that can serve as the target of the LEAQ. Right, so they're saying at the time that we're about to call it, we need to load its address into something that can be used to do the jump or the call. Okay, so the output of this pass, which is the monadic form of the funref language, extends the monadic form of the language with allocations, with funref and apply in the grammar for expression, augments programs to include a list of function definitions. So basically, let me make a commit on this first. Yeah. I'm going to add uncover get to the UI. Okay. And then we're going to look at what we had before. So there was L-alloc, right, was the language that we were translating from previously, and then L-mon-alloc has these atomic things, right? So I think what we need to do, let's look at what they say in these tables. Okay, so that's C fun. Let's look at 7.7. Okay, so the types are carried through. Funref and apply are expressions, but apply takes a list, it takes an atomic for the function ref, and a list of atomics for arguments. Okay, so the question is, hi Chris, great to see you. Important question, is your GPU okay? I saw it like burning or something. I sure hope it is. Okay, so yes, this is a similar form. The water block has the issue. I'm very sorry to hear that. As effective as water cooling is, it has a lot of intrinsic dangers, doesn't it? Card itself is technically fine. Water block corroded though. Oof. So I'm guessing that's something we're gonna have to remove that and replace it, and be out of commission for a while. Not fun. Okay. So I'm trying to think about which direction do we go? Like, do we take this, which is very concise, and duplicate it and add the things to it, or do we take this, which of course has our formatting bits in it, and do the conversion to atomics? And I think the answer is that we take this and add things to it. I think that's what we want to do. Oh wow, it's only a 2080. Yeah. Well, I hope you're able to get one at a GPU that you like at a decent price. They are not cheap right now, and some of that has to do with the fact that RAM's not cheap, and everybody wants GPUs for AI, duh. Okay, so what I'm going to do is the latter. We're going to do, this is going to be Elmon Funref, right? And we'll add these things to it. So we're going to change this to Elfun. Yeah, that has the types in it. Okay. Oh, that's not so bad. 350 for a GTX 5060, or is that RTX? I don't know. The thing. I work for that company. I don't understand the product line. Yeah, definitely not paying $3K for a card right now. I did see, I don't know if they're still running it, but Micro Center was selling DGX Sparks for like $4,000. Bear in mind though that those are not Intel machines; they're ARM. I think they're a Grace CPU in them, but not exactly a gaming machine, or could be a good development machine though if you're doing graphics. Okay, but it's not a Mac. If you're bound to Macs like I am, would not be good. Okay, so we have the type. We don't need to worry about that. So expression, we need to add funref, which is going to be basically the same stuff as we had in our other thing. So why don't let's just grab funref. That's easy. I don't have to redefine it. And then apply. So apply is going to be, the function is going to be atomic. And oh my goodness. Yeah, it's really out of control, isn't it? The price of GPUs nowadays. Okay, and then the arguments are going to be list of atomic. And the program, we also have to copy over the whole definition bit. So I'm going to get that out of here. It's going to be the same. And then this is going to be, program is going to be defs list of definition. Okay. The only bits that we have left that I'd like to handle is the formatting. So we haven't, I don't know that we've done one at this level yet, because we don't have remove complex operands in our UI. Oh, okay. Yeah, luckily PCs for gaming and Linux Windows for testing, Mac for work. Yep. Okay. So what I'm going to do, and this is going to, yeah, let's get this. We're going to put it up here at the top. I hate copying all of this stuff, but I really do want to make sure that, probably going to need that stuff too. I want to make sure that we have the pretty print. Now that it's easy to reproduce, I want to make sure that we have the pretty printing everywhere. The cost is, you know, copy it. But copy, modify, right? Okay, so we need to do, import that. Let's figure out what all the other breakages are. Okay, we need format type. Let's see, what's the next thing that it's complaining about? Okay, so now we need to fix these case clauses. Format expression. I think the key realization here is that let's move this up, because those are going to be wrapped in atomic. I'm going to say if let's rename that. I don't like it being named. Let's just say condition. I think that's the only place it's referred to. Okay, so those are expressions. That doesn't have to be atomic. Explicate control will deal with that. Okay, so I think that what we'll do here is let's do it like this. Let's not make a specific thing for atomics. We just know that these we're going to wrap that like that. And then we need atomic void. I think that's the missing one. Hey, that clears up a lot. Let's go down here. Okay, so we're going to say this is atomic. So it's interesting. Funref is not atomic. Oh, right, but it'll have to be a variable, right? Okay. So all I'm doing here is simplifying some of our I'm rewrapping these, even though we know they're atomic, so that we don't have to write another, like we don't have to write format atomic. I don't think that that's really necessary. You know what? I'm changing my mind. Let's make format atomic. And we're going to do, this is going to be format atomic. Generate that function, please. Where did it go? Okay, format atomic. Okay, so we'll do case, except it's not function, it's going to be a. Int, we'll do int, it's actually going to be doc from string int to string value from string var name. We'll take this, put that there. Okay, and then has type, this is going to be, I want to grab this stuff that we did up here, and then we'll collapse that. Where's the has type? Okay. Okay, and this is going to be format atomic. And we'll just drop that out. Okay, so now that we have that, let's go up here, and I'm just going to say we're going to get rid of these clauses, and we're going to say this is format atomic. Okay. And then that should resolve most everything. Let's go down here. Okay, so now these things where the primitive operations have atomics and not expressions, those can be use that. Really mechanical changes here. Yeah, those are all the same problem. Okay, and vector is not a thing here. Okay, and void is no longer an express or a primitive operation. Hold on. There's no or and in primop. So those have been turned to ifs. Okay, and let's make sure that this is named correctly. Labels, value, okay, value, easy enough. Hello, okay. Right, okay, so this has a reduced set of primitives. Because remember that or and were turned to if by the shrink phase, so we don't need them as a primitive operation. Okay. Okay, so we can build and compile. Now let's go to remove complex operands, the crux of this. And we are going to use lfun. This needs to be lfunref, lmon,lalloc funref, was it? Yeah, alloc funref. And this is lmon funref. Okay, so now we need to fix these. This program is now a set of definitions, so or a list of definitions. So what we need to do is basically what this does, but for each definition. So this is going to look really familiar to what we did before. And let's move this in here, and we'll say this is def.body. And then we have def l. So we need to turn this into lmon definitions. Def.name. Let's see. So definition has the arguments, okay. Def.arguments, return, and then the body is going to be that. So let's just rename it to that. So we're both performing this pass on the body of each function, but also converting to the new definition type. Okay, now we have a lot to do. So this has two mutually recursive functions, where you call RCO atom on something that has to be atomic. So like an expression that needs to be turned into atomic, and basically what it does is it looks at that and it says, I'm going to return an atomic, and then if there are any bindings to be made, this is the expression to the variable that should be bound, and then I'm keeping a counter because we're making temporary variables for all the bindings. So yeah, so like for this, this is a complex expression. So this says well, if I call RCO atom on this, I'm going to get 42, the integer 42, right? If I call RC atom on this, it's going to return, hey, here's the variable to put in the place of that expression. And then, you know, this is I did it as represented as a dictionary here, but it's just a list because the order of binding is important. Of binding the temp.1 variable to the expression negate integer 10. And this becomes a let, and so forth, like so. Okay. So, really what we need to do here is just have it fill out the missing patterns. So for funref, we need let new var, new counter is new var for counter. And then we'll return elmon var for the new var. And then our binding will be new var is elmon.funref name arity. And then new counter. Okay, so that one was really simple. That's just saying if we have a funref, we need to put that reference into a variable. That's the LEAQ instruction we'll come into later, and then bind that variable to that expression. Okay. Apply also. So we're assuming that, well, we're not assuming. So function here is an expression, and in the output we need it to be atomic. So let's do, I want to look and see if there's any other things where we do them in particular orders. Yeah, so we do map fold here, right? On begin. We'll want to do something similar. We want to do something similar for apply. So let's do the function first. So if we do RCO expression, that's going to be right. It's going to return an atomic, a list of bindings and a counter. Okay, so we're going to say function bind f bindings counter RCO atom of function and counter. And I'm not gonna I'm just gonna rebind this. I don't know why we did this new counter 1, counter 2, so forth. I'm just gonna rebind it, and then we're gonna say map fold like we did above. Over arguments, and that's going to take counter as the accumulator, right? Okay. And this is going to be, and we have, because I put these in the different order, we're going to have to do pair swap again. I think that we did that up above. Yeah, pair swap RCO expression S. Except we need these to be atomic, so this needs to be RCO atom. Yeah, that's not going to be sufficient. So actually, what we need here. Think about this more carefully. We need the counter, and we need the bindings, and I want to almost like. Let's look at the list module, because maybe there's something else that we can do here. Nope, list please. Okay, so we were using map fold. I guess that's okay. Just that reconstructing the accumulator is going to be expensive. Okay, so we return the accumulator type and the item type. Okay, so this is going to be, we'll just call it accumulator. Bindings is going to be this is going to be counter bindings, argument bindings. Sorry, bear with me here. I'm coming up with the structure here. So we start with an empty list. And then I think that what we will do is we're going to say the atomic, the bindings, and the counter is RCO atom, because these need to be atomic. And we're going to pass the argument, and then we're going to pass for the accumulator the counter, and then right, okay, so this is going to be our new counter, and then we'll do list append to accumulator 1. The problem with this is it's technically expensive. I just want the bindings to come out in the correct order. And atomic. Okay. Okay, so now it's just complaining those aren't used. But we should see the list is, or the result is correct. That's a list of, yeah, strings to expressions. That should be a list of atomics. The main thing I don't want is for these to come out in the wrong order, or these to come out in the wrong order. Because what we're going to do now is we're going to say this is going to be L dot. Oh, we need to make a new variable. New var counter. Okay. And then this is going to be new var. And what we're going to do is we're going to say, excuse me, we're going to append, we're going to do multiple appends here. We're going to take the function bindings, and we're going to append the argument bindings, and then we're going to append the new variable that we made. New var is going to be lmon.apply. Did I not get that correct? Lmon fun ref. Yeah. Okay. Okay, apply function arguments. Okay, what's wrong here? Oh, we need to go lmon.var. Okay. Yeah, we did that right above. I don't know why I got that wrong. Okay, so just to review what we're doing. In lmon apply, the function is an atomic and the arguments are atomic. So what we need to do is turn the function into an atomic, right? So if that introduces any bindings, which probably will, then we have an atomic here, which is a variable probably, and then any bindings that this sub-expression contained. And then we need to do the same for each of the arguments. And then we make a variable for this particular apply expression, because it is not atomic either. So now we've introduced this new variable. We collect all the bindings. So starting with the function and then the arguments, because if those are not bound, then we cannot bind this apply. And then we have the binding for the apply and our updated counter. Okay, so now we need to go through here and we need to add the missing patterns. So this is an expression. So if we're in expression position, we don't need to do anything with this one. We just need to translate it to the new thing. And that's just this and counter, because we don't change it. Okay, and then what we're going to do here is yeah, I'm looking at this and I did something similar here. We just did a bunch of appends. And then you fold right with lets. So here, if we have apply an expression position, right, so what we would do is something similar to what we did before. Counter. So we know that this has to be atomic. And then we're going to do counter A bindings. We'll use that map fold again. And honestly, we can just copy this from up here, right? The difference is that we don't need apply to be atomic, so we don't need to generate a fresh variable for it, but we can just copy this. keep that to do there for now. Okay, so then we do something like this. We're going to take F bindings, and we're going to list append A bindings, and we'll do list fold right. With the accumulator is lmon.apply function arguments, right? Because we've already turned those into atomics. And then we'll say expression pair, and this is lmon.let pair.0, pair.1 expression, and this is just getting the wrapping it all up, right? Expression counter. Okay, I'm going to rename this to apply, just so we're clear there. So just to review what this does, so we've collected all the bindings, right? And what we're going to do is we're going to put this apply way on the inside of a bunch of lets, and that we will wrap those in reverse order so that the last argument gets bound last, and then the very first thing that gets bound is the function name, the function atomic, and yeah, that's it. I say that's it, but like the brain, getting the brain there is the hard part, right? So what we're going to do now is everybody's favorite, uncomment what used to be there. So this is fine, except that this doesn't, these are the wrong types now. So we're going to have to update these tests. Yeah. And it's that easy. Well, so it's not. But I think what's nice about this incremental approach is that we're not really changing any patterns. We're just adding new small features every time we start a new chapter, and the patterns mostly stay the same. I think that's a sign of a good design, is that you can incrementally improve it like this, and that like we could say, oh, what did we do in the past for where we had a bunch of things that we needed to generate bindings for and wrap them around? Well, we did this thing, and so I can just copy paste that and it works, right? That is super nice. Yeah. So the fact that I've like kind of kept things named the same. So we're gonna do this rename like we did before. And this is lfun. And then we need to do a decent amount of work here. I think this test will be easy to change, but I'm wondering about some of the other ones. Right, so like order bindings matters. We need to make sure that that's preserved. You know, if does not require atomics in the condition position. Loops is interesting. Tuples. Okay, so we have used this parsed helper thing in other places, but we need to update it with the new phases and the new styles. So I'm going to go back to, where's our uncover get test? And we're going to, whoa, that was some lag. We're going to copy paste that because one of the things, so I used that thing that did the automatic transformation. But it didn't do well with the pipeline of should be okays. So it left some weirdness in there. Okay, and let's just use those qualified. Are we even using that? Oh. We probably should. I wonder if I should go back and add that here. So it's not just like, does it parse? Maybe we could say this is untyped, and then we could let assert, okay, AST is let's see. Type check program. I wonder if that'll break things. Like this one is already broken, but yeah, let's put that in our helper down here. Let assert okay AST type check program. That's just I think that's an essential extra layer of safety for our tests. The only thing that may be weird about it is there will be certain things where, well, what does this has type bit, right? That's okay. We're good with that, I think. All right, let's go back to the top and start fixing this stuff. So, our input program here, we need to make a definition. So I think that we're going to be doing this mechanical transformation multiple times. So we're going to say L definition main empty integer t, and then the expression. Okay, and then we'll do the same thing down here. And I think that I might want to, rather than referring to that, because that name can change over time, I think I want to import that type or that constructor. So we're going to get integer t in here. Okay, and this needs to be Lmon definition. Okay, so conceivably we could run that test and see if it still works. And let's, for the sake of speed here, let's just paste. And we'll do the same here, except we'll say Lmon. And Not, like I've said many times, not really interesting content, but we're making it work. We're making progress. And the compiler is helping us. By that I mean the Gleam compiler is helping us along the way, which is also important. Okay. All right. So this be Elmon. And then we go down here and we put that. Okay, so I have no idea if this is going to work. Let's find out. And then we'll figure out what's different. Okay, so the big problem here is we have cases where we have L-toop. Oh, I haven't updated this. Okay, I jumped the gun there. I thought we were at the end. We aren't. Okay. Woof. Okay, so actually, these are type issues. So I think that what I want to do is, and probably what happened is I had it like pretty print this, and we need to just import this. So let's import all the type variants. Boolean t, void t. Okay. And then we'll find L-toop. And we'll replace that with nothing. And let's see what's wrong there. Okay, so we're not using void t. That's fine. Okay, and we need to import equal. What else is wrong here? I think that's it. Let's run Gleam test. Okay, so at the very least, we didn't break anything. But we haven't tested anything new. So we need to come up with a test for, and I think what we'll use is their example from the book. Let's come up with a test that we can make assertions on for remove complex operands. And where's that example they gave? Yeah, here we go. So this example, we've used it before. That might be too complicated. We might want to use that one that was shown in the tail calls section. But let's go RCO apply funref test. Okay, so we're going to say let p is parsed, and we'll put that program in there. just want to get this looking decent so we know what's going on. Okay, so this is map, this is main, this is inc. And then, so what sorts of things should we look for? I think that we should look for in main probably is the easiest place to look. We should see something like let temp.1 is map, right? Because a function ref is an expression. And then, and I'm sorry, this needs the weird way they do let. It needs that. Okay, and then we'll have another let, which is temp.2 of inc, right? And then we'll have another let there's actually going to be more lets than that because vector construction is very complicated. But I think the main things that I want to look for there is that in the main function we start with a let binding, and the binding is the function ref map, and then inside that immediately is another let binding where the function ref is inc. And then we should see some of the vector construction code. And then we should see another let, which is the apply, because vector ref has to have atomics, right? So that apply will be bound to something, and then vector ref and 1 will be the innermost expression. That's probably a good place to start. So let's say we're going to just pass that to remove complex operands. I don't think that we need to know what the original looks like, although it might be interesting. Let's do an echo here first, so that we get that printed out, and then we'll have the resulting program. Okay, and then we're going to say let assert okay, our main function is going to be list find in p.defs okay, so we want the main function. And then we want to see let's just do this as a let asserts, right? lmon.let, and then the variable name is probably going to be temp.1, right? The binding is going to be lmon.funref. Why am I not getting that? Map, and that takes 2 arguments. And then we'll say that, and then we'll do another let assert here, which is lmon.let temp.2 lmon.funref inc 1 inner, and so forth. Okay, so this is not D, this is main.body. Okay, that's a good start at this test, and that kind of covers the stuff. And we'll echo vec here. I want to get some output on this test so that we can see what the heck's going on. Okay, so it passed, which is good. Yeah, there's like all these like empty bindings where it's vector set that field and so forth. That's not really that useful. Right, so this is initialize the fields and initialize it with 0 and 41, and then you're checking, there's all the garbage collection tests, etc. Yeah. Okay. So, the next bit that we should probably test, I'm sorry, I keep flipping programs when I actually want to do something different. We should see what happens with, because this is a function, it's already in a variable, so there won't be a binding introduced for it. The other problem is, I think that, you know, there's going to be the vec-init bits. So we should probably, yeah, let's go ahead and get the, you know, the ink is not going to be changed because that's an atomic, that's an atomic. That function's not going to be any different. So we could just check that we could look at the body and say elmon dot prim plus var, and this is going to be uniqueified, so that's going to be x.1 elmon dot int 1 ink.body. So we can check that, and that's just to show that this is already atomic expressions, and so this function should be no complex expressions, should be equivalent to what we pasted above, right? Okay. And then, you know, okay, this might be a case for introducing snapshot tests. Somebody had mentioned that in a previous stream. I think it could be useful as these examples get more complicated. Snapshot tests could help. The problem is you have to be able to read the snapshot that is made and make sure it's okay. Here we're actually saying we're expecting these particular things to happen because, hey, this is, you know, we're doing an apply in here, and so you need to, you know, function ref is complex, so that needs to be put in a let binding. Those are some, and since this is an argument, that needs to be, and it's complex, it needs to be put in a let binding. We know vector is complex, it'll be put in a let binding already. So we're just checking that, you know, both the function and the arguments in the apply expression are getting turned into atomics. I think that's the essence of what we want to do here. So what I'm going to do is map. So in this case, f is already an atomic as a variable, so that will not be transformed. But we should see a let binding for vector ref for each of those. Yeah. Okay. I believe that's the case. So vector ref, right, because V in the origin language is an expression, so that has to become atomic. In our case, that will already be atomic. And then the index is, in the case of this example, is an integer, so there'd be no let bindings generated for that. But up here, we'll be calling RCO atom. Which will follow this case. Right. Okay. Cool. Let us write that out. Okay, so we're going to say let assert okay map is list find, and we'll do the same thing. I almost should make a helper function for that. Call it find def. Okay, so we're gonna say assert, we'll do let assert again. And we'll say temp.1 is that correct? Okay, so we expect it to assign a temporary variable for this vector ref. Let's run that test. Okay, so it failed. Oh, well, I pulled out the wrong function, so let's look at map. What? What line? 421. Okay, so just name the variable differently. That's fine. Okay, so it actually has let. That's interesting. Oh, right, because it's going to do, it's trying to get, I was partially right. So it's trying to initialize the first field in that vector. And then it's going to go down into here. Right, so that is should be correct now. Okay, we're still not correct. Prim vector ref. Oh, we have the has type, right? Okay, so let's fix that. That's fine. We're carrying that has type maybe longer than we need to, but that's okay. And I need to make sure I import. Oh, I got those. Okay. Okay, now it passes. Let's go ahead and look at the rest of this output and like see if it makes sense. So yeah, so here, note that what comes right after we've bound that temp1 is apply F1 to temp1. So I think that that's probably worth putting in here. As, hey, we're going to say this is vec init, and then we'll run the apply. Since this is already atomic, right? We don't need to do any transformation to it. It's all good. And I don't think that we need to include the rest of that. It's just, it's useful to show that, you know, we're doing the transformation correctly. Okay, we're almost at time. I wanted to get to explicate control today, but we might not get to it. Let's have a look at what will come next. Let me use page down instead of the wheel. Okay. Remember, this is just a callback to say that those function references are assigned to something, and we're using indirect function calls in this calling, in this code gen. So that's why they need to be in variables. Okay. Limit functions, explicate control. Okay, so let's look at this, and then we'll start this next time. In the meantime, let me get all of this committed. And this is chapter 7.6. Remove complex operands. Elmon fun ref language. Okay. Okay, so yeah, okay, so explicate control. So far we've been working in expression-based languages. And remember, if you've seen the other chapters that we've done, explicate control goes from expression-based into basically imperative. And they call this 3-address form, and that really comes down to there's a left-hand side and then there's a right-hand side which has 2 addresses in it. Essentially that's what it is. And so you have a sequence of assignments, or return is the basics of it. Now we have expanded upon that. Like, so if we look at ctup, which is what we did for the last chapter where we introduced heap variables, the essence of a program is you have, you know, some blocks, And those each block is, so it has a name and a tail, and a tail is either return a sequence of statements with another tail. So we're still kind of representing this as expressions, but like this seek is kind of like a console. You can think of it like that. A go to or an if. And then statements are either assign, the read statement, which is like read something from the console but throw it away, vector set, which we saw in the previous language, or collect, which is a call to the garbage collector. So assign is assign to a variable an expression, and the expression is either an atomic, just like we've seen before, so one of these things, a primitive operation, and this is where you get the 3 address code thing, or allocate, so allocate a number of slots of a particular type, and that type is, I think, really just to carry forward. The amount is actually what we care about, and then a global variable is like similar to the global value we have over here. So it's things like, where is our heap pointer, where's the start of our heap and the end of our heap, and stuff like that. So those are for interacting with the garbage collector. And but you can see that like the form there is not a bunch of expressions from which you implicitly return the tail of that expression, but instead a sequence of assignments or returns. So yeah, this is very much like imperative, put some things someplace and then eventually jump somewhere, or return a value. So what are we doing here? Okay, so they're changing the abstract syntax for C fun. The auxiliary functions for assignment and tail context should be updated with cases for apply and funref. And the function for predicate context, so assignment context is this. So if we want to, if this expression is going to be assigned to something, this is assignment context. I kind of want to keep that up so we can point to it. Tail context is something that is a sequence or a return. So tail context is you're looking at one of these. The function for predicate context, that's the if. So, and really only the expression part of the if. So this explicate control has different functions that apply to each individual spot in the generation. Okay, so predicate context should be updated for apply but not funref, because a funref cannot be a Boolean, but an apply could return a Boolean, right? Because we'd be calling a function. Okay, in assignment and predicate context, apply becomes call. Okay, so let's look at that. So expressions include, so we would add to expressions funref or call, and call only contains atomics, just like what we did in the past that we implemented today. And then a tail can be a tail call. So that's with particular, so you could really only call the same function. We're not allowing mutual, or are we? I don't know. Regardless, these would be the arguments to the tail call. and that would eventually get transformed into a goto. Okay, and then definitions, and then so the program is again a list of definitions, and so that definition is a label, the arguments, the return type, some arbitrary info, which they don't say that what we're going to use that for, and then a set of blocks, which are labels with tail expressions. And those labels are about the decomposition of loops and branches and so forth. Note that this has no loop expression in it. It has goto. So it has to generate labels for that. The interesting thing here is that because this is a goto, that when we adjust explicate control, we're probably going to have to carry our counter for unique labels through all of the definitions. So that'll be interesting. I also wonder if, and we'll see, if this transformation means that the label for this definition becomes a label for the entry point inside the function. Let's continue reading and then we'll wrap up for the day. Okay, in assignment predicate context, apply becomes call, right? Whereas in tail position, apply becomes tail call. Okay. So that makes sense because tail position is always you're going to return something, or you're going to branch, or you are going to, yeah. So like tail call becomes a variant of tail. That makes sense. Interestingly, that means that because like a tail call is implicitly returning control or passing control to the function that you're calling without returning yourself. That to me says that this would like maybe trivially implement mutual tail recursion, because if this is turned into tail call, whatever you call next takes over the current stack frame, and then you don't create a new one. Interesting. Okay, so we recommend defining a new auxiliary function for processing function definitions. This code is similar to the case for program in LTOOP, because LTOOP didn't have functions, it only had one expression. The top level explicate control functions that handles program defs form for lfun can then apply this new function to all the function definitions. So it's basically saying, like, that each definition has one expression in it. So use the transformation we did before in explicate control. Yeah, treating the body of each definition as a tail. Okay. That makes sense. Okay, and then they jump immediately to select instructions. So again, they're not giving us a ton of detail here. We'll need to jump into that next time and figure out what we need to do. So this will be a brand new, we'll have a brand new language, the C fun language, and we'll have to redo a bunch of explicate control. But I think it'll be, or I'm hoping it'll be straightforward. There will probably be things that will be interesting that we haven't considered before, so we'll have to take those into consideration. Anyway, thank you all for hanging out, and we'll see you next week.